In the previous investigations, we learned what it means for a relationship to be a function, how to use and interpret function notation, and we evaluated functions and solved equations involving functions. In this investigation, we will continue to develop our understanding of function notation and think about how to represent and interpret new functions as modifications of previously defined functions. To explore this idea, consider the following context. In a galaxy far, far away, two planets rotate around a sun. It takes both planets 32 days to make one full trip around the sun, and planet B is always 2 times as far from the sun as planet A is. Let's examine the planets as they make one full revolution around the sun. Let's let the variable t represent the number of days since we started observing the planets. Given any value of t, there's exactly one corresponding value for planet A's distance from the sun, so planet A's distance from the sun is a function of the number of days since we started observing. Let's call this function f, so that f of t represents planet A's distance from the sun in light years. Similarly, planet B's distance from the sun is a function of the number of days since we started observing, so let's let the function g represent planet B's distance from the sun in light years in terms of t. Since planet B is always 2 times as far from the sun as planet A, for any value of t, g of t must be 2 times as large as f of t. And we can actually think about this visually. So let's draw a segment from the sun to planet A, and the length of the segment represents the value of f of t. And as the planets rotate, this value of f of t is going to vary. Now if we draw a segment to represent g of t, it'll go from the sun to planet B, and this new segment should be 2 times as long as the previous one we drew. And this is because planet B is 2 times as far away from the sun as planet A. And as the planets rotate, the segment representing g of t will be 2 times as long as the one representing f of t. And since g of t is always 2 times as large as f of t, we can write the formula g of t equals 2 times f of t to express g of t in terms of f of t. So let's look at a graph. We'll plot t on the horizontal axis and the distance from the sun in light years on the vertical axis. Now, if we do this, we can plot the functions f and g on the same set of axes. We've got the graph of function f here and the graph of function g up here. Now it looks like the graph of function g is sort of a stretched version of function f. We didn't really do any stretching, so let's examine why it looks like g is just a stretched version of f. If we pick any value for t, maybe we'll pick t right here, we can examine the corresponding value of f of t. So we'll draw a segment to represent f of t, and we know that g of t must be 2 times as large. So if we drew a segment that's 2 times as long as the previous one I just drew, it'll be about that long. And because of this, the point on the graph of g at this value of t is going to be 2 times as far above the horizontal axis as the one for f. So given any value of t, the value or the point on the graph of g at that value of t is going to be 2 times as far away from the horizontal axis as the one for f. Now, we could use the graphs of f and g to determine the domains of f and g, but I'll leave that to you if you're interested. For the rest of this investigation, we will be looking at scenarios where we can slightly modify functions to create new functions that model other quantities within the same context.